Hello everyone, welcome to this online course on material science. This is lecture 8 in the module 1 on magnetism. If you recall, in the last lecture I have started talking about the concepts of quantum mechanics required to understand magnetism, and I have mentioned few basics idea. Let me quickly recall those ideas here. So I said that any quantum mechanical state usually represented by a kate vector, say psi, in this angular bracket, and then once we have some kate vector, we can also define the corresponding bra vector denoted by the angular bracket pointing left. So once we have some kate and some bra vector, we can talk about defining an inner product between them, which will give us a number. So if you want to define the inner product between this bra and this kate, so we will put the bra on the left and kate on the right. That's the inner product between the bra psi and the kate psi. And we also talked about that in order to get the wave function from the state psi, we need to perform the inner product with the coordinate r, bra vector, and the state vector psi. So this will give us the wave function as a function of the spatial coordinate x, y, z, denoted by this r vector. And then we talked about the operators in quantum mechanics, and I mentioned that usually the operators are represented by the hat on it. And let's say we are talking about the energy of the system, then E will be the energy, and hat means is the energy operator. And it's customary to call the energy operator by the name Hamiltonian operator, right? And Hamiltonian, the name derived from the famous Irish mathematician Hamilton, right? And once we have this operator, the question is, how do we find out its value, right? Because as I have mentioned, operators in this raw form do not have any value. That's the topic of this lecture. This will come in a couple of minutes. And then in the last lecture, I have also mentioned a number of operators that will be encountered in the diamagnetic discussion, like the position operator, the momentum operator, then the potential energy operator, the kinetic energy operator, the angular momentum operator, right? And then I have mentioned that usually the operators operate on a state vector and produce another state vector, right? I mean, some operator A operating on some kate vector, say phi, and it will produce some other, usually kate vector, which is a state of a vector, a state of a system psi. So those are the basics that I have discussed in the last lecture. Now, in this lecture, let us start with a very important concept of the wave function, right? The psi r denoted in the last lecture. The first comment that I want to make is that this wave function need not to be a function of the space r only, right? Because I have told that already that this could be a function of a space, which is x, y, z, time, and also the spin of particles, right? Usually it turns out that the space and the time dependent are not that difficult to understand. So once we have the spatial form of the wave function, right, the spatial dependence of the wave function, we can add this time and the spin index later. That's why in this course, most of the time I will be talking about the wave function depending only the space coordinate x, y, and z. But to explain the understanding of the wave function, let's assume the wave function here is depending on the space and also on the time, but not on the spin. Now, what is the physical meaning of this quantity? The first important point to understand is this wave function is a complex number. That's one very crucial point, because in a real world, what is this complex wave function represents is not that easy to understand. It seems, if you look at the history of like quantum mechanics, when Schrödinger wrote down his famous equation, right, involving this wave function, he really didn't understand what the real meaning of this wave function, right? He solved the problem of hydrogen energy calculation using his equation, but even then, It turns out that Max Born came and he really interpreted the wave function correctly, right? And that's called the probabilistic interpretation of the wave function. So the wave function has something to do with the probability. We will see it. But the important thing is that, as I have said just a minute ago, that the wave function is a complex number. There should be a way to find a real number, right? So usually when you have a complex quantity, the way to get a real number out of it, it's to form its modulus square, right? So we need to perform a modulus square operation on the wave function to get something real. So this is, by definition, this product of the conjugate wave function times the wave function itself, right? This is the real number. Now, how to relate this real number with the physical quantity of interest? Let's say this wave function psi rt represents a wave function for a particle moving in the space in 3 dimensions, right? And let us assume that we have a volume space of cubic form, and every side is dx, right? So dx, dx, and dx. So the volume element has volume dv. This can be also written in shorthand, this d cube x, or like dr. They are the same. Now, if one asks the question that what is the probability of finding that particle in this dv volume, then the probability that we will find the particle inside this small volume element is nothing but the volume element times the modulus square of the wave function. So the wave function modulus square is giving us the probability of finding the particle inside a finite volume. That's really the key understanding of the wave function, which first Born interpreted it in this way. So let me summarize. The wave function is a complex number. You need to form the modulus square to get a real number, and once you have the modulus square of that wave function, you have to multiply it with the, you need some volume element to find the probability, right? And now assume the particle is real, so the particle has to be somewhere in this space, right, in real space. So if you integrate this quantity over the whole space, right, all the probabilities need to be added up, and you know the adding up all the probabilities must give you number 1, right? So you need to integrate this over the whole space. This condition that the modulus square of the wave function when integrated over the whole space should give you 1 is called the condition of normalization. So these things are really for you, it's a set of rules. Don't worry about them too much, but I just want you to know that these things exist, and these terms like normalizable wave function, what it means that if you have some wave function, you can form a modulus square and then perform this integration. It should turn out to be 1 if the wave function is normalizable. Okay. Then next topic that I want to introduce here is the concept of the commutator of operators. This is very important and will become useful in the study of magnetism. So let us assume we have 2 operators, say A and B. Now question is that how do you define the operation commutator between these 2 operators? The way we define is like A comma B in the square bracket. This is by definition is A, we need to put the hat here, minus the reverse order B times A. Physically what it means, if 2 operators are commuting with each other, meaning let's say A and B, commutator is 0. What it means is that AB is minus AB is equal to the BA, right? Sorry, BA. So the order can be changed. That's the important message. If two operator commutes, meaning that A, B operator is commutator is 0, then you can interchange the order of the operator. That's the central point. But if the commutator is not 0, you cannot change the order, right? Because they are not 0, and then you need to take special care. So there are some operators which commute within their self, and then we can change their order. For example, when we study diamagnetism, there will be operators like position operator and momentum operator. So here I want to give you some rules about this commutator. Let's assume some electron in 3 dimensions, right? The motion is in 3 dimensions. That's why we'll be needing the vector R operator, which has 3 components, right? X hat, we have Y hat, and Z hat. And also we have this momentum operator in 3 dimensions. It has 3 components, Px hat, we have Py hat, we have Pz hat, right? Now let me give you the commutation relation with R and P. So one thing to note that X Px, Y with Py, Z with Pz, these are like the pairs are known as canonical pairs for reasons in the originated in classical mechanics. But the important thing is that when you are trying to form the commutator between these canonical pairs, they are non-zero. But if you want to form the commutator between, select X with Py or X with Pz, they are 0. So let me give you the set of rules which will become handy for us. Let's say the operator X and Px. So they are canonical pair. You can show this is non-zero and the value is IH bar. H bar is the reduced Planck constant, right? Similarly for Y and Z. For Py, we have I times H, which is, it means that for this canonical Z times Pz, for these canonical pairs, we cannot interchange the order, right? Xpx is not equal to Pxx, Ypy is not equal to Pyy, and Zpz, you cannot change the order, Pzz, right? They are not equivalent. But any other combination between the position and the momentum, like say, for example, let's pick X with Py, right? Or let's say X with Pz, they are 0. So you can change Xpy, Pyx. This can be interchanged. You can interchange X with Pz. So when the operators commute, you can interchange. That's the basic information that I want to get across, that commuting observables can be interchanged, right? This calculation will be useful in deriving the diamagnetic expression at some point in the next lectures. So remember this, and let me give you the one last final equation about this commutation. Usually all of this relation can be summarized with this single expression, that the commutator between Xi and Pj is IH times the Kronecker delta. And you know what is Kronecker delta is. If the index are different, it is 0. But if the index are same, it is 1, right? So meaning, if the pairs are not the same, the xpx, ypy, if they are not canonical pairs, we will get 0. And if they're canonical, then we will get IH bar, right? Makes sense. This is like the summary of the commutation. That's all you need to know. There are some deep consequences of this. Just let me mention just one. If you remember the Heisenberg uncertainty principle, right? It says that you cannot measure two quantities at the same time with arbitrary precision, right? Like the position and the momentum. You have to know that which position and which momentum. Usually, the fact is that if you want to measure the canonical pairs like position x and the corresponding px momentum, then Heisenberg uncertainty principle applies there, right? You cannot measure them with arbitrary precision. That's why for non-commutating observables, Heisenberg principle applies. But if the operators commute, right, there is no Heisenberg uncertainty principle. Like for example, xpy, if you want to measure the x position and the y component of the momentum, you can measure them with arbitrary precision, right? This is very important. There are the deep consequences, but let's not worry about them for this course. And the last topic that I want to introduce here is known as the expectation value of the operators, right? And as I've mentioned before, that the need for the expectation value is that usually in quantum mechanics, the operator in the raw form doesn't have any value, but we need some values from the operators. So the way and the answer to this question is how to find out the values from the operator is the expectation value, right? Let me define first the notation first. Let's say we have some operator which is O hat. O stands for operator, and if I put an angular bracket on the both sides, this represents an expectation value of the operator O. And next question is, how do you calculate this quantity? For that, you need two things. You need to know the form of the operator, which operator you're talking about. Or you also need the state in which you want to measure this expectation value. Let's say the state is some k vector psi. Having these two things in your hand, then you can talk about this expectation value, where you have to sandwich your operator between the ket psi and the bra psi. And as I've mentioned before, that expectation value of the operator is the value of that operator, right? So this should produce a number depending on what the operator is, right? And can you see that this should be a number based on what you have already know? Let's see. So if you look at this part of the expression, what's happening here? There is a ket, and on that ket, an operator is operating on, right? Let's say when operator O operates on psi, it gives you, say for example, some other ket phi. That's this part, and this part is left alone, untouched, right? What's that? That's an inner product between the ket vector phi and the bra vector psi. And we already know this must be a number, right? So it's consistent with the definition. That's nice. And in the context of diamagnetism, right, let me introduce this notation in the context of in the next topic. So in the diamagnetism, usually what we concern is that we have some motion of electrons inside the atom, and we want to study the motion, right? So for very simple case, let's assume that around some proton, electron is moving, right? And assume that the electron is in its ground state. So what that means, in that path, the energy of the electron is minimum, right? So usually the ground state ket is denoted by this 0 ket. That's the ground state of the electron. So you have your ground state. Now the question to ask, what you want to calculate? Usually the most important thing, as I have mentioned before, is the energy of the system. And the energy, the corresponding operator, is usually known as the Hamiltonian operator, right? That's why usually you will be asked to calculate the operator Hamiltonian, its expectation value in the ground state. The question is, if you understand this part of the discussion, this is nothing but you have to form the bra of the ground state, you have to sandwich the operator in between, and then the ket vector, right? That's the expectation value of the energy, usually denoted by, in the short form, in this angular bracket. That's how you find out the value corresponding to any operator, right? And before I finish, I want to mention some notational point about this expectation value, that every time you see some bra vector, let's say psi, and some operator, let's say O and psi, this is always, just remember it, an integral calculation. We know this is a value for this number for sure, right? But another interpretation, this is an integration. The way you perform this integration is very interesting, right? Let me illustrate this fact. The integration here you need to perform, you have to ask yourself first, what is the ket? The ket is psi, right? Okay, so we have a ket psi. The question is, what is the corresponding wave function? You would say, of course, the corresponding wave function is psi r. And we are assuming here that the wave function is not dependent on time, only space r. And we are not caring about the spin at all. Then I will ask, what is the bra vector? In this case, the bra vector is the psi, right? Also. Then you have to ask, what is its corresponding wave function? Let me give you the rule. If the ket produces psi r, then the bra will produce its complex conjugate. That's the rule you remember. There are reasons why this works, but let me give you this way. The rule is, for the ket, the wave function is psi. For the bra, it's the complex conjugated, right? So have a look at this operator. On the left, you have a bra. So you start with conjugated wave function. Then you have the operator itself. Then you have the ket, which is the corresponding wave function. So you write this and you perform the integration over the space. That's the expectation value in notation, and that's the integration you need to perform when you do some simulation, right? In computer, you need to set up that integration. What it says, this operator is operating on this function. That's like another wave function, and then you have to multiply the complex conjugate of psi r, integrate out this thing. This is a number, right? Once you perform the integration, this must be a number. I hope everything is consistent now, right? That this is what this expectation means. And before I finish, another notational point is that what is this quantity then, right? An inner product between the bra psi and the ket psi, right? This is the bra psi, this is the ket psi. Following this rule, you ask yourself, what is the ket? You know ket is the psi, so corresponding wave function should be psi r. What is the bra vector? That's also psi. Then what is the corresponding wave function? You have to complex conjugate it, right? So if you look at this thing, this is also a number, right? That's why this must be another integration. So the way to read it, that for the bra, you need to put the complex conjugated wave function. For the ket, the wave function itself, you multiply these two and you perform the integration over the whole space, right? This is an integration, and if you remember this quantity, this is nothing but the modulus square of the wave function, right? And we have just talked about this. This is the probability of finding the particle in all space, let's say. When this quantity is 1, we say the wave function is normalized. So the summary is, in the Dirac bracket notation, the normalization condition is simply this. I hope this makes sense to you, and this will be useful in our discussion in the coming lectures. So if you want to understand these things in more detail, you can have a look in this book by Cohen Tanuzzi and others. And I think that's about it, and thanks for listening.